Thank you very much for the introduction, and I would like to thank the organizers for the invitation and the opportunity to give a talk at this conference. I would like to talk about the project that originated a few years ago, so it will be a kind of an overview of some old, some new results. And I will talk about an approach to the study of the dynamical systems that are known only from data. And our methods allow for global conclusions about the dynamics on the basis of finite samples, with the emphasis on applications to sparse data sets. Traditional analytical approach to dynamical systems is possible only when a mathematical model of the system is available. In many situations, as we know, in particular in biological sciences, sociological sciences, or medical sciences, this is rarely the case. Instead, the scientists can collect data, and then there's a question how to make global conclusions on the basis of such a finite information. In this context, methods and theories of interpreting the data are needed, and in particular topological methods attract interest. Topological invariants can be particularly useful because they are robust. Traditional focus of dynamical systems is on understanding the structure of invariant sets. However, correctly identifying the invariant sets may require capturing the generator of the system with an extremely high level of precision, which is often impossible given a finite amount of data. Therefore, our approach focuses on coarsely characterizing the dynamics rather than finding the underlying generator of the system. And our characterization is done via the Conley index, an algebraic topological invariant, from which we can induce the existence and the structure of invariant sets, for instance, the existence of fixed points, periodic orbits, heteroklinic corrections, or chaotic dynamics. By a finite sample of the dynamical system, I mean a finite subset of the phase space, together with either approximate images under the generator of the system with discrete time, or a finite collection of vectors at each of those points that indicate the direction of a sampled flow. Today I will focus on the first case. So in this case, from data we can in a pretty natural way construct a multi-valued map. So what we do, we discretize the space, we bin the data, because at the end of the day we would like to the computations to be feasible, so we would like to have everything finite. So for instance, we can construct a cubical map. We look at cube and sample elements that fall into this cube. We look at the images of those points in the phase space, and in order to define the value of the multi-valued map of this element, we cover by cubes the images of those points. This is not enough, because we would like to be able to go to homological computation. So we would be happy to have cyclic values of the multi-valued map. So we should add something to these sets. In some of our approaches, we use the so-called sunflower enclosure. Namely, we consider a convex hull of those points, and cover by grid elements this convex hull. Okay, and we proceed with each cube in the phase space. Then we go to edges. When we go to edges, we look at cofaces, all the sample points, the images, convex hull, and so on, and then to vertices. In such a way, we define a multi-valued map, which is cubical, which has, of course, compact values, and which is upper semi-continuous. So, our strategy is as follows. From the data, we construct a multi-valued map. Then we find isolated invariant sets and topological invariants such as Conley index, Conley Moss decomposition, Conley Moss decomposition, Conley Moss graph. Everything for this multi-valued map, which is a tool, which is just a tool. And then we try to relate the obtained results for this multi-valued map with the underlying dynamics. Let me say a little bit more about some specifics of our construction of the multi-valued map. So let me switch for a moment to simplest possible one-dimensional case, because I would like to present graph of such a map. So here the phase space is just interval 0, 1. Okay, and the data are marked in blue. So we cover the images by grid elements. Then we end up with such a blue set, and this set is meant to coarsely represent the continuous, the graph of the continuous generator of the system. So in this context, this set is not perfect because the domain is connected and the image is not. So what people usually do, they expand the values of the multi-valued map in such a way that there exists a continuous selector of such a map. But, so this is this expansion in red, but then we can see that each continuous selector of this red multi-valued map has a fixed point 1/2, while using this multi-valued map in red, we cannot isolate this set. We cannot identify this set using this multi-valued map in red. This is because, for instance, the identity is one of the selectors, so we cannot isolate anything. Okay. So again, this is not a good tool for us. But so let's step back to this blue set. In fact, we don't need continuous selectors at all. What we need is to be able to do the homology computations. So acyclicity, as I already mentioned, is enough. So in this one-dimensional case, this is pretty obvious that we achieve that when we add to the value at 1/2 the interval. And this is our multi-valued map, which quite properly can identify at least the fixed point at 1/2. Okay, because it's pretty easy to see that, for instance, this interval in orange is an isolating neighborhood for this fixed point. So what I wanted to emphasize is that we end up with a multi-valued map, but usually this map has no continuous selector. Otherwise, when we try to have continuous selectors, we pretty easily lose the isolation. Okay. Yeah. The multi-valued map is used here in our strategy just as a tool. So what we claim then is that the Conley index computations that we run for multi-valued map are valid for a class of single-valued maps, and this class is just the class of approximations. Of continuous approximations on the graph of capital F of this multi-valued map. Here is the definition of this approximation. So our claim is, and I will show you a result which tells about that. The claim is that the Conley index computation that we make for multi-valued map is valid for approximations, for single-valued approximations of this multi-valued map, with some quantification of the region of this approximation. Okay. Now about a little bit about the Conley index. So assume that we have an upper semi-continuous map with compact values, and this map will be used as a generator of the dynamical system. First definition is the definition of a solution, namely a sequence sigma is a solution for capital F through X is if it goes to X, and sigma of n plus 1 belongs to F of sigma of n. So here we have inclusion instead of the equality as in the classical case. And this is very important because this means that for multi-valued dynamical system we have no uniqueness of forward solutions. We have multiple forward solutions. And we define an invariant part of given set N as a set of such points that there exists a solution, which stays in N and goes through X. So only the existence is imposed here. There may be other solutions that leave this set N, but in order to claim that X is in an invariant part of N, the existence of such a solution is in. Okay. And a very important, the Conley theory notion of isolating neighborhoods. So literally this notion is exactly the same as in a single-valued case. Namely, we say that N is isolating neighborhood for F when its invariant part is included in the interior of F. Literally the same, but the fact that we have multiple forward solutions makes the notion a little bit different, I mean, in the consequences. And this is pretty obvious that set S is invariant with respect to F if it's equal to its invariant part. And this set is called isolated invariant if it admits isolating neighborhoods that such that S is invariant part of its neighborhood. And the main tool in the construction of the Conley index is the notion of a weak index pair. So the notion of index pair. Index pair organizes the dynamics inside isolating neighborhood, but it turns out that in multi-valued case, isolating neighborhoods don't need admit index pairs, and even our toy example shows that. Namely, this is one of the axioms in the definition of an ordinary index pair, namely that the image of P1 minus P2 is a subset of N. Look at the image of this invariant set is interval 0, 1, so there is no chance to be included in any isolating neighborhood. So the ordinary index pairs are no longer useful for us in the case of multivariate dynamics. Therefore, we introduce the other notion, the notion of so-called weak index pair. Okay, so a pair of sets, of compact sets, is called weak index pair if those sets are positively invariant with respect to n. Invariant part of n is included in the interior. Here is the picture which we can look at. And we assume also that P1 minus P2 is included in the difference between P1 and those P2 is in the interior of n. This is the definition of a weak index pair, and it's pretty easy to see that such a weak index pair in this isolating neighborhood exists. You can take as P1 the whole isolating neighborhood and the endpoints of this interval as P2. It's easily seen that the axioms are satisfied. Okay, and what is important, what we proved, that isolating neighborhoods for the multivariate dynamics admit weak index pairs. So each isolating neighborhood we can find a weak index pair, and moreover, when we take an so we can find a weak index pair which is let's say arbitrarily tight isolates the invariant part of the set. So when we start with a given neighborhood of invariant part of the invariant set, then there exists a weak index pair such that P1 minus P2 is a subset of that. Okay? And using weak index pairs, we were able to construct the Conley index. Namely, how it works, how we define the Conley index. So let P be a weak index pair. By the positive invariance of those sets P1, P2, we can observe that F restricted to P maps this pair P into pair T of P. What is this pair? Namely P1 plus everything which is outside N, P1 plus everything outside, P2 plus everything outside. So the restriction of capital F to P is a map of pairs. The inclusion, because the difference between those two sets is just P1 minus P2, so the inclusion of P into T of P induces an isomorphism in the Alexander-Spanier cohomology, because this is the consequence of a strong excision property. So we can define so-called index map. What is the index map? Namely, this is the inverse of map of this isomorphism induced by identity, composed with the map induced by F restricted to the pair P. Here is the assumption that our map has acyclic values. Okay, so which guarantees that we have maps induced in cohomology. And then we apply the Lerner functor. This is a kind of normal functor to the cohomology module of P, and this index pair to this pair the Lerner functor. And what we obtain is a graded module with its automorphism, and we call this module the Lerner reduction of the Alexander-Spanier cohomology of index pair. And this module, by definition, is the cohomological Conley index of the invariant set. And what is very important here for the definition to be correct is, and we proved that the Conley index does not depend on the choice of isolating neighborhood. and that does not depend on the choice of the weak index pair. So any isolating neighborhood admits weak index pair, so it doesn't matter which isolating neighborhood we choose, which weak index pair, what we compute is the same. And now, what about the relation between the Conley index results for multi-valued map and epsilon approximations? So we relate those things using properties of the Conley index. This is what is important here is the continuation property of the Conley index. So we similarly as in single valued case, this is the theorem. Namely, if we have if lambda is a compact interval and f lambda is a parameterized family of discrete multi-valued dynamical system, so the as long as when we change lambda as isolating neighborhood remains, the Conley index does not depend on lambda. So it's similar result as for single valued case. And using this result, we can prove that there exists in the setting as before, there exists an epsilon, positive constant epsilon, such that the set of epsilon approximations of our map, which is compact and cyclic valued and approximately continuous. So the set of approximations is non-empty, and for any continuous epsilon approximation, small f, this epsilon approximation shares the Conley index with the multi-valued one. So here we have existence in a general case. In case when the map is cubical, we can quantify this epsilon. Namely, we can strengthen the result and we can prove that for cubical maps, the above holds for any epsilon less than 1/2 delta, where delta is a grid space. Okay. Yeah. How we can use the Conley index to identify, let's say, orbits, for instance, periodic orbits. Assume that isolating neighborhood decomposes as a pairwise disjoint union of compact sets, and assume that we are interested in some trajectory which is in those sets in green in some order, for instance in such an order. How we can prove that such an orbit exists? Namely, we use the following construction of so-called extended space. Namely, we consider copies of those space, as many as the number of pieces of N that we would like to visit. So formally, we take ZP, the topological group with addition modulo P and discrete topology, and this X bar is the Cartesian format of those guys, and we define new dynamical system on this new extended space in the following way. Namely, the image via F bar of Xi is f of x, but on the next copy of the space. Okay, so when we are interested in some trajectory, the sequence sigma will denote the numbers of those pieces that we would like to visit. Then what we do, namely, we can define a set for this sequence. We choose first element in the first level, the second one in the second, and the third one here. Okay, so we define such a set, and S sigma denotes the invariant part of this N sigma. The important thing is that we can talk about the dynamics of the new space using the Conley index computations in the original one in the following sense. I mean, we can define the homomorphism of products of modules associated with those weak index pairs. So here is the definition. This is inclusion. This is index map in the original space for F, and this is projection. Probably it's easier to think about this definition about this map using its matrix representation. So what we do, namely, we would like to have transition between sigma 0, sigma 1. So from sigma 1 to sigma 2, here we put the block of the matrix of the index map, which corresponds to this transition between sigma I plus 1, sigma I in the opposite direction, because we use the cohomology functor which is contravariant. Okay, so here is the piece of the original matrix which is responsible for transition between sigma 1, sigma 2, sigma 2, sigma 1, and so on and so on. So a kind of an artificial homomorphism, but constructed just from the matrix of the original index map.
Sorry, this X is product?
Product, yeah.
Tensor product?
It's a product. Just a Gaussian product.
It's a product. The pi. So
Yeah. Yeah. And what is important about this sigma I, namely, we can prove that S sigma, I mean, S sigma, as already defined, is isolated invariant set. This set in blue is isolating neighborhood of this set, and we can find in this isolating neighborhood, we can find a weak index pair for this set and this dynamical system, such that iterates of order P of this artificial map sigma pi and iterate of the index map in this space are conjugate. So this is a technical result, but it tells us that actually everything what we would like to do with the Conley index in this space can be extracted just from the Conley index from the original one. Topological. Yeah. Okay, and as a consequence, we can use the previous proposition to claim that if this homomorphism I sigma is not nilpotent, then there exists a trajectory that visits those pieces in a prescribed order. And in order to prove that, we just use the Warzewski property of the Conley index in this space, but we don't need to go through this space in practice, because we know that if I sigma is not nilpotent, then also this guy is not nilpotent. So this tells us that we have a trajectory which visits. So there is the invariant part of this set in blue is non-empty. Then by the construction of the dynamics, it means that anything what stays in blue must go through those guys in a prescribed order. So this is how it works. And we also can define endomorphism in applications. This is easier. Namely, from the index map, we can just select a column with index I, and the similar result can be proved that, namely, if the composition of those endomorphisms, here is the sequence that we are interested in. If this composition is not nilpotent, then there exists a trajectory that visits those sets in a given order. And we can strengthen our results, namely we can claim that our trajectory is periodic when we assume that the Lefschetz constant of those iterates, all Lefschetz constant of this composition is not trivial. Okay. Let me skip the discussion about the proof here. We use the Lefschetz type fixed point theorem by Srebnitsky because of the time. And let me tell also a few words about topological semi-conjugacy. Namely, here is the definition of transition matrix, which is pretty well known. We define Lefschetz completeness, namely we say that homomorphism is Lefschetz complete if such a composition, if the Lefschetz number of such a composition is non-trivial for any sequence which is admissible with respect to the transition matrix, for any sequence, and we also assume that this matrix A is irreducible. I mean, the graph associated with this matrix is strongly connected. So, what we can prove under the setting as before, if the index map in the original space is Lefschetz complete with respect to a given decomposition, then there exists a semi-conjugacy between the original dynamics and the shift dynamics on a finite set of symbols. Moreover, for each periodic sequence, if the set of admissible sequences, there exists a periodic point f in the pre-image of this conjugacy. Okay. And similar result in the language of compositions of those homomorphisms G, namely if this composition is not nilpotent but for any sequence which is admissible with respect to the transition matrix. So if you have this nilpotency, not nilpotency, then there exists a semi-conjugacy also. Now, since we don't assume anything about the Lefschetz completeness, we don't claim about the periodicity of trajectories. So this is our machinery, and now some applications. I have several applications, some of them for Henon map, when we can detect chaotic dynamics. Let me skip those results and mention just one of the results, which is, I assume, maybe more interesting because it uses data from physical experiments. So let me skip the other results. If time permits, I can go back to those applications. So we tried our approach for physical data set coming from so-called magnetoelastic ribbon experiment. Short experimental setup is as follows, namely a ribbon is a thin strip of material which is clamped from at the bottom and placed in the uniform magnetic field, and also the oscillating magnetic field was applied, and depending on the strength of the uniform field and the frequency and strength of the oscillating field, and also on the physical properties of this material, the strip may exhibit variety of motions. In particular, it may be chaotic. And the position of this strip was measured, and we have 100,000 of numbers collected from this experiment. So we used this time series. Actually, we use elements from 30,000 of those numbers. And what we do, namely, we try to embed to make the representation in R3. Namely, we take triples of our points and define on this set transition shift map, shift by one. Why we use this map? This is because of the Taken's theorem, which gives us the hope that using this technique we can reconstruct the dynamics, the underlying dynamics. And we take some binning. This is the size of the cube that we used. And for this map, we constructed the sunflower enclosure capital F map. And from now on, we do the Conley index computations for this multi-valued map. And here we can see the graph of this multi-valued map that we constructed. We are able to find isolating neighborhood in green that consists of three pairwise disjoint sets. Here is weak index pair. Magenta is red is P1, and red plus magenta is P. Sorry, red is P2 and red plus magenta is P1. So this is a weak index pair. This is what we identified, and we made Conley index computations for this map and obtained such a transition graph. And our theory that I already presented allows us to claim that the set of epsilon approximations where epsilon is a half of the grid space is of this multi-valued map is non-empty. Moreover, this compact set N is an isolating neighborhood for any of such approximations, and there exists a semi-conjugacy between small f and the shift dynamics on three symbols, and for each periodic sequence we have a periodic point in the pre-image, and in particular we can compute the topological entropy, which is positive in this case, so it indicates that we have chaotic dynamics. Okay, so this is how it works. And here is again for the same data set, but representation in 2D. Again, we were able to prove the chaotic dynamics. And now let me say that the effectiveness of this approach, of course, depends heavily on the data set that we have. It depends on the size of values of multi-valued map, which depends on the grid size, and this in turn depends on this resolution depends on the amount of data available. What we see which is pretty natural from experimental, when the grid is too granular, we get only very close representation of the dynamics, and the finite the grid is, the more details of the dynamic can be identified. So the sample size is a limitation in practice because, as indicated here, we can try to go to finer and finer meshes to obtain more detailed results, but when the sample is finite, at some point we have to stop, because here we cannot subdivide this box, because we end up with some boxes with no sample elements, and we cannot construct them the volume map. So, but at the same time, the machine learning development is advanced, and there are techniques that can fit surrogate model to the data with high accuracy. And so we tried to adapt methods from both the Gaussian process theory and the classical Conley index theory to samplet dynamics. And this is what I would like to present now, is done in collaboration with Marcio Gameiro, Ling Hang, William Kallis, and Konstantin Mishaikov, when we tried to use Gaussian processes combined with our techniques. So let me say a few words about this surrogate modeling. So in principle, the strategy is very obvious, is straightforward. Namely, we have data which we use to train the Gaussian process. Okay? We estimate the parameters. Then we use the Gaussian process to construct the multi-valued map. Then we apply the Conley index machinery to it. Okay, so this is how it works. So here is the assumption, namely we assume that our data set consists of points x, y. Y is the image of f. F is an unknown continuous function which is assumed to be a realization from a Gaussian process with some pre-specified semi-positive kernel with some vector of unknown parameters. So the data are indicated by red dots here on the right-hand side. In first step, given the data, we estimate parameters and we construct the Gaussian process model. So we obtain a mean of this process and a covariance function. Mean is indicated as a black curve here. Then we choose some finite cell complex whose geometric realization is CW complex is our space X. So in this case, this is just uniform decomposition of the interval into sub-intervals, but in general, it can be any CW complex. And we construct multi-valued map. We require that G is a geometric realization of products of cells, and that for each point G of X, the value is non-empty and constructible. And we use, so let's step back. So this construction in this, for this example, is this map whose graph is in blue here. This is our multi-valued map. So then we use the combinatorial representation of this map to identify potential dynamics and compute Conley indices. Since computations are made for this multi-valued map in blue, the inclusion, this inclusion yields a confidence level. This means that the Gaussian process is a subset of this set G. This inclusion yields confidence level of our computations. And since we are interested in high confident result, we try to modify this set G to both preserve the dynamics and maximize this probability. So this is the idea. And this is our main theorem, which is a kind of asymptotic. Namely, we assume that we have IID data from the uniform distribution, and alpha is responsible for the diameters of the values of the multi-valued map. Delta is responsible for confidence. So we can prove that when we take fine enough discretization, I mean the diameter of cells is less than epsilon 0, and we take large enough data set, n is greater than n0, then we have both, namely probability that the supremum of diameters is less than alpha, and the probability that Gaussian process is included in this constructed G is greater than 1 minus delta. So this theorem says basically that we have two fundamental results, namely that the detailed dynamics can be extracted from capital G, as the fibers of the graph of this map can be arbitrarily small with high confidence. And the second, that the dynamics that we identify occurs since sample path of Gaussian process are included in G with high confidence. Okay, so this is our result. And few words about how we construct this map. So our construction is in principle dimension independent. So what we do in RD, namely we look at the function f, the generator of the system, component-wise. So when we assume that f is the realization from a Gaussian process, it means that we have Gaussian L components of this, D components of this map, and we use D Gaussian processes for each component map 1. And here we have some parameters. This is the mean, this is the overall variance, and some vector of parameters in the kernel. First, as I said, we estimate the parameters. So any estimation method can be used, but we used maximum likelihood estimators for our parameters. So here are the formulas for those guys. We can find them analytically for beta and for sigma, for theta numerically. And when we once the parameters are estimated, we can make predictions from a Gaussian process. So we have a mean, as we compose this mean from the means of those Gaussian processes in each coordinate. Here are the formulas for those means and variances. What is the prediction from the Gaussian process at a given point? This is just a conditional distribution prediction. It takes form of a conditional distribution given the data set. Okay, so that are standard conditional expectation and standard conditional variance. Okay, and recall that any multivariate normal distribution, random variable with multivariate normal distribution, Then the squared Mahalanobis distance from Z to the mean has known distribution, and this distribution is chi-squared. So, okay. So Mahalanobis distance has this distribution, and this applies for our Gaussian process prediction also. So we can take a ball in the sense of the Mahalanobis squared distance. Here is this ball, which takes form of an ellipsoid. Okay, so when we take as a radius of this ball the quantile of order 1 minus delta of chi-squared distribution, then we know that the probability that G at x belongs to this guy is greater than 1 minus delta. Okay, so we call such a ball, such an ellipsoid, a confidence ellipsoid. Okay. And this is pretty straightforward, namely, when we have an arbitrary finite set S and some confidence 1 minus delta, then we can pick confidence ellipsoid, one at each point V, such that the total probability that the Gaussian process has each of those guys falls into the corresponding ellipsoid is greater than 1 minus delta. Okay? And since we would like to make this multi-valued map that we are going to construct a confident representation of the Gaussian process, we insist that all such confidence ellipsoids or subsets of values of this multi-valued map that we construct. Okay? For a given set, for instance, for the set of vertices in this decomposition. What about the rest of the points in the space? We use the properties of the kernel. So in our approach, we restrict to kernels that have so-called high probability bounds on partial derivatives. This property have kernels which are 4 times differentiable. For instance, Gaussian kernel or Matern kernel with parameter value v greater than 2. From this high probability bounds on partial derivatives property, we can induce the following, which roughly says that Gaussian process, sample path of a Gaussian process is Lipschitz continuous with constant L, that the probability that this inequality, Lipschitz inequality, holds is greater than this term. Okay, here we have this L on the right hand side, so we can see that when we enlarge capital L, the probability quite quickly goes to 1. Okay. So this is the property that we use in the construction. Let me skip the general case. I think more important is intuition behind this construction. So let me go for a moment to the simplest possible case, I mean one-dimensional case. So imagine that we have an interval and we would like to construct a multi-valued map from a sample. We divide this interval uniformly into sub-intervals. So we have vertices, we have edges, and consider the set S as the set of midpoints of but only of odd-numbered intervals. Okay, so this is this set, and in this set of midpoints, we, for a given delta, we can find from a Gaussian process tuned to the data, we can find confidence intervals large enough such that the probability that the midpoints, that the images through the Gaussian process fall into those intervals is in total greater than 1 minus delta half. Okay? And in the first step, we can define values of the multi-valued map in odd-numbered intervals. So we just cover by grid elements those confidence intervals. Okay, so we are guaranteed that with probability at least 1 minus delta half, that the Gaussian process falls at the midpoints, falls into the black lines, hence falls also into those blue regions. Okay. Now, in the second step, we take capital L large enough. This is parameter of our construction in applications, but here we can take from the high probability bond property of partial derivatives of the Gaussian process, we can take L large enough so that the probability that this is a proper Lipschitz constant is again greater than 1 minus delta half. And at each of those intervals, we put lines with slope L and minus L to the left and to the right, the top and on the bottom. So we can think about those regions as Lipschitz cones. So what we know? We know that with high confidence, the Gaussian process lies in the region between those red lines. So now the definition for the rest of the points is pretty obvious. Namely, we cover those regions by values of the multi-valued map. So what we get. So this in blue is the graph of our constructed multi-valued map. What we know that with probability greater than 1 minus delta, Gaussian process lies between those red lines. So is epsilon half approximation of our map in blue. Okay. And we already know that then we are able to make Conley intensification about the dynamics from the multi-valued map. And here is an example of how it works, how our construction depends on parameters. Again, just to share the intuition, one-dimensional case for logistic map. What we do, we take logistic map with this value of parameters, so we know the dynamics of this map. Maybe we have two fixed, unstable fixed points, and other initial condition limit in two-period orbit gamma. Okay. So what we do, we take some points from the logistic map as our sample. We forget that we used this map to sample. From the sample, we construct the Gaussian process with Gaussian kernel. We take as a parameter some value, capital L. As I remember, L is equal here something like 8 to be large enough to at least cover the sampled map. And this is what we get for confidence 95%, and we divide this interval into 2 to power 10 sub-intervals. And when we make Conley index computation, then we can see that we can identify here an attractor, which is correct, but it does not present all the details that we expected, because we expected to see here in this set 2 periodic orbits, so we don't see that with given confidence and this resolution that we choose. So what we can do, we can go to final mesh, still for the same confidence. We run the computations again, the construction and now we have twice more confidence intervals, so the construction from the very beginning. And now we can see here the Conley index indicates that we have 2 periodic orbits. Okay. One can ask, can we claim the existence of this 2 periodic orbit with higher confidence? So we can increase the confidence level and repeat the construction. Here is the result. The result, it says no. With higher confidence, we don't see 2 periodic orbit. So probably we could take final mesh. But actually I tried some other way, namely we require that the total confidence of confidence intervals is 1 minus delta half, but we don't need to take the same, uniform confidence for all intervals. So we can play in such a way, since we already see that something interesting happens here. Here we have some invariant set. Let's try to look deeper in this set. So what we do, I try to, over this interval of interest, I try to use shorter confidence intervals. I think that it is, I hope that it is visible, that the graph is changed here, yeah. In order to keep the total confidence, I needed to enlarge confidence in the intervals elsewhere, so we can see that this map has huge values somewhere else. But it turns out that it was enough to detect the 2 periodic orbit again, without going to the final. Okay, I have some other examples, some other applications, but I think that I'm running out of the time, so let me stop here. Thank you very much.